Hello everyone, this is the first video and only video from chapter 31, and we'll be talking about electromagnetic waves and polarization in these two sections in night. So we want to look at E&M waves a little bit more quantitatively, and so this practice problem has, it gives us the electric field as a function of position. We want to find the magnetic field as a function of position. So you'll notice a couple properties right away. So one thing is that it looks like E&M waves are transverse waves. So notice how our wave is a function of ky plus omega t. So this says that this wave in particular is traveling in the minus y direction. But the disturbance, the electric field, is pointing in the plus x direction. So disturbance is perpendicular to the direction of wave travel. Remember, that was for transverse waves, not which is unlike longitudinal waves. So this is more like a wave on a string than like a longitudinal wave. But we need to look at a few more properties before we can say what the magnetic field vector looks like based on this electric field vector. Okay, so we're skipping a lot of the previous sections. It's summed up in this number 1 right here for properties. Maxwell's equations predict the existence of sinusoidal E&M waves that travel through space independent of any charges or currents. Okay, so we know that, so we've already said that, you know, light waves exist and they travel at the speed of light, but this is where we're actually bringing in the electric and magnetic fields into this. The waves are transverse waves, which is what we hinted at here, with E and B perpendicular to the direction of propagation. Okay, let me draw a picture of that property right there. So we have a light bulb right here, which let's focus on a light wave that's traveling to the right here. So that means that so the electric field here, so at this point on the light wave, the electric field could be anywhere in this plane. So there's a plane that's perpendicular to the light. So the electric field could be up, it could be out of the page, could be down, could be any combination, a little bit up and a little bit out of the page. Let's say the electric field is exactly up at this point right here. If that's the case, if the electric field is up, then I know that from the direction of the light wave and the direction of the electric field, I know that the magnetic field has to be out of the page at that point. So the only reason I drew it down here was that, well, I guess I could draw it right here. So that magnetic field is into the page. So B is into the page, or sorry, out of page, if the electric field is up. And notice how, so how did I know to draw it that way? I know that E cross B has to point in the direction of the wave. So notice how with E up, I have to choose B out of the page in order for them to be mutually orthogonal, and for E cross B to point in the direction of the light wave. So if you look on the left right here, that's exactly what property numbers 2 and 3 have to do with. So E and B are perpendicular to the direction of propagation, and they're perpendicular to each other. Okay, but for a wave, they're also, these directions are changing in time and in space. So first let's focus on in space. So if we look a half a wavelength later, which for visible light is like a couple hundred nanometers, if we look half a wavelength later, the electric field is pointing down, and the magnetic field, therefore, has to be going into the page. So B would be into the page right there. So notice how still, if you use your right hand, E cross B is still pointing to the right. So if E is down, B is into the page. If E is up, B is out of the page. So again, E cross B is to the right here. And your book has a much better visualization of this than I can do. So your book is describing an E&M wave that's traveling in the plus x direction. Anytime E is in the plus y, B is in the plus z. So y cross z is equal to x. And if E is in the minus y, then B is in the minus z. And again, E cross B is still in the x direction. So these pictures are showing the change over distance, but it's also true over time. So if we waited a half a period, then this electric field would point down. Oh, I do that in a way that it'll be really hard to erase. There we go. And the other one will be pointing up. the electric field would be pointing up. So remember that these are oscillating not only in space, but in time. Right? Half a wavelength versus half a period. The electric field will reverse direction in either of those two cases. Okay, number 4, all E&M waves travel at the speed of light. That you're used to. C is 3 times 10 to the 8, 3.00 times 10 to the 8 meters per second. So what your book went over in previous sections was that actually you can derive this speed from the permittivity and permeability of free space. So this 1 over square root of epsilon naught mu naught. So you might recognize those quantities from E&M. You can derive this 3 times 10 to the 8 from that. Finally, we can relate the amplitude of these two things. So this right here, is the amplitude of the electric field, E naught, 300 volts per meter, for example, for this particular problem. So if we know the amplitude of the electric field, we know the amplitude of the magnetic field. They're related by E equals CB at every point on the wave. Okay. And notice how these are also in phase. So when E is 0, B is 0. When E is a maximum, B is a maximum, etc. So let's use all of these facts. We want to use all of these properties to do this problem that we have up here. Okay, so let's do the problem, the original problem. Okay, the magnetic field. So the fact that these are in phase means that when E is a maximum, B is a maximum. So we're going to have some amplitude that we'll write down in just a second. But the fact that if we plugged in y equals 0 and t equals 0, E is a maximum. So that's where B is a maximum. So in other words, this fact that they're in phase means that we can copy down this part exactly the same. So cosine ky plus omega t. Okay, so it'll be the same wave number, same frequency in there. So this direction will be different and the amplitude will be different. Okay, so first let's do the amplitude. So B is equal to E over C. Right? That's exactly what this equation is saying right here. So if we divide both sides on the left here, if we divide both sides by C, we get that B is, looks like it's 300 volts per meter divided by 3 times 10 to the 8 meters per second. So you might wonder, well, what the heck is a volt times second divided by meters squared? But that's probably not the best unit. The fact is we have SI units for electric field, SI units for C, so that gives us SI units for magnetic field. So this answer is going to be in Tesla. So 3 times 10 to the 2 divided by 3 times 10 to the 8. It looks like it's 1 times 10 to the minus 6. So this is 1 microtesla. Okay, great. So that gives us the magnetic field amplitude. Then what about this piece? What goes in right here? So this you really need to practice your right-hand rule. So let's draw a picture here. So we know from this info right here that the wave is traveling in the minus y direction. Okay, so I'm going to set up a coordinate system here. X, Y, and Z will be out of the page. Okay, so I'm going to try and fill in the details here. So the wave is traveling in the minus y direction, right? We know that from this piece right here. And also we're told that at this instant in time, so at, for example, y equals 0 and t equals 0, E is pointing in the plus x direction. Okay, so the electric field will be pointing in the plus x direction. So this will be the direction of E. So we need to choose B so that the magnetic field B is perpendicular to both the direction of the light and E. And the direction needs to also be such that E cross B is pointing down, right, in the minus y direction. So it's either going to be out of the page or into the page. So try and pause and think about it right now before I give you the answer. Okay, so we can think of this by maybe just guess and check. So if B was into the page, E cross B, so you take your right hand, right cross into the page would be up. But that's not what we want, right? We want the light to go down. So it looks like we have to choose B out of the page. B has to be going this way. So now, if you do the right-hand rule, right cross out of the page as your thumb pointing down, and that's perfect. So B needs to be pointing in the plus Z direction. If y equals 0 and t equals 0, this is going to be in the plus Z direction. Okay. So we found out, so our overall answer then is B is equal to 1 microtesla. That's the amplitude. We're in phase with the electric field, so this part is exactly the same, ky plus omega t. So it's going to have the same wave number and same frequency as the electric field, right? Because they're describing the same wave, the same light. And then the direction here is going to be plus z. Okay, so this will be our answer right here. Okay. Now, so that's the relationship between electric magnetic field and the direction of the light. The light carries energy, and there's a nice formula to describe the energy flow, and this is called the pointing vector. So this person's name was Poynting, P-O-Y-N-T-I-N-G, and they were kind of destined in life to describe the direction of energy flow. So the person's name was Poynting, and they discovered something about the way that the energy points. It's a neat coincidence. So at any point in space, you have so E cross B is the direction that the light is going. That's also the direction the energy is going. So it probably doesn't surprise you that E cross B is in the direction of energy flow. And actually, for the units of energy, so if you do E cross B divided by mu naught, that actually gives you something related to energy. It's not quite an energy, but it's a power. Okay, so the units, the dimensions here are, sorry, not quite power, but power per unit area. This is going to be intensity. So this is power per unit area, or in other words, intensity. So SI units of this, so as long as you plug in volts per meter, Tesla, and then the 4 pi times 10 to the minus 7, whatever the SI units are for mu naught. Overall, the SI units here would be watts per square meter. Okay. Now, E and B are functions of time. So, and they're sinusoidal functions of time, and they're in phase. So actually, it makes more sense. It's nicer for us to talk about average intensity. So for E and M waves, they have frequencies that are very, very, very high. Right, the period of an E and M wave is very, very, very short, for like 10 to the minus 14 seconds, or something, something like that order of magnitude. So it makes a lot more sense to talk about the average pointing vector and the magnitude of the average here. This is average over time. So the average value of this is actually the maximum value for the electric field times the maximum value for the magnetic field divided by 2. And then the mu naught comes along for the red. So the reason for that is that the electric field and the magnetic field both go they're both like a cosine. So if you have cosine squared and you take the average value over time, then you get a 1/2. So if you plug in the amplitude of the electric field, the amplitude of the magnetic field, and divide by 2, then this is the average intensity. This is the average pointing vector, or the intensity of the E and M wave. So this tells you how much energy is being transported by an E and M wave, and how it relates to the electric field strength and the magnetic field strength. Okay, so one common example at this point is you take the intensity at the Earth's surface, so 1400 watts per square meter. That would be this value of I due to sunlight at the Earth's surface, 1400 watts per square meter. And you can solve for how big the electric field is, what the electric field amplitude at the Earth's surface is. And your book, by the way, writes this, and you can write it, so because E equals C times B, you can write this just in terms of the magnetic field or just in terms of the electric field. So that's what your book does right here with writing it a couple different ways. Or you could write mu naught in terms of C and epsilon naught, etc. So there's a whole bunch of things you can do here. Okay. So then you can also talk about, well, the intensity should drop off like 1 over r squared. So that tells you what you can do with, so that tells you how the electric field also drops off in space. If you had, for example, a light bulb like this, and the light is spreading out over 4 pi r squared. That tells you how quickly the electric field is going down. Okay. One last thing is that you can talk about pressure. So like if you have a laser pointer shining on you, it's much more efficient at transporting energy than it is momentum. Right? From sunlight, you're never like blown backwards from sunlight. You know, you're not pushed back. You're more likely to get a sunburn because of the energy and not be moved around. So you can actually calculate what the pressure is, the force per unit area, and it's related to this intensity right here. So this intensity, if you just divide by the speed of light, you get radiation pressure. So a closely related thing to energy is forces and pressures. So the pressure of an EM wave, P, so P radiation, this is like a lowercase p for pressure. And this is if the EM radiation is absorbed. This is I over C. If the radiation pressure is reflected, then you get twice as much force, right? Just from Newton's third law, right? If the light is bouncing back in the direction it came from, then it gives even more of a boost. So this would be 2I over C. Your book only gives the absorbed value, but the reflected value is just twice as much. Right? So your book talks about solar sailing. There are some ideas for launching spacecraft and using sunlight to actually push on a spacecraft. But you would need a pretty big area. That's the point of this question. You would need a really huge area to get a force that is substantial. Okay, so and then your book talks a little bit about antennas. So a changing electric and magnetic field will set up E&M waves, and that's exactly how an antenna will transmit signals. So it's this oscillating electric and magnetic field that transmit EM waves. Okay, last thing, polarization. So I mentioned before, we talked about an example with the electric field pointing in a certain direction. So really, so again, the same light bulb here. So maybe for one photon, the electric field is pointing up. For another photon, it's pointing out of the page. The electric field is pointing out of the page. Totally unpolarized. There's no, each new photon has a totally separate direction of the electric field. But if we require, I'm imagining that the light is going to the right here. So we can force the light to pass through what's called a polarizer. And that will force the electric field to only have one component. So rather than, if the light's going to the right, the electric field has to either be up, down, or into or out of the page, or some linear combination of the two. But this polarizer can force the electric field to have to be up or down. So after this polarizer, there's no electric field that's into or out of the page. Okay, so a polarizer can be as simple as just a metal grating. So generally it's like made of polymers that, in order to filter out things on the order of the wavelength, right? Because you got to get pretty small there. But it's basically like a metal grating, just super small. And there's two important properties quantitatively. So when you have a polarizer, you're blocking out some light from getting through. Polarizer. So if you're blocking some out, then the intensity that gets through is not going to be as big. Okay. So there are two rules for how much the intensity drops off after the light goes through a polarizer. So two rules here. So the first rule is that if you have unpolarized light, of intensity, my handwriting is getting worse and worse as the quarter goes on. Intensity, I not. Its intensity after passing through the polarizer is 1/2 I naught. Okay, so like light from a light bulb will be unpolarized. If there was no reason for it to be polarized initially, it's unpolarized. You pass it through the polarizer, only half of the energy gets through. Energy per unit time, per unit area. So that'll be intensity. Only half the intensity gets through. The second rule is called the law of Malus, or Malus's law. And this says that if you have initially, so suppose you had unpolarized light, and then you pass it through a polarizer. So now the light is polarized. So remember, only half of the intensity gets through. Okay, so suppose you had intensity 2 I naught, and then after it passes through the first polarizer, its intensity is I naught. If you pass the light through another polarizer, where the axis of polarization is at some angle theta relative to the first one, right? So we're polarizing the light first, and then we're polarizing it again. Then the intensity of the light that gets through is going to be even less. And it drops off by a factor cosine squared theta. Okay, so this means that if you pass light through a polarizer and then through another polarizer that's perpendicular to the first one, you can get light that you can totally block out all the light. And so your book has an example of this right here. So it has two polarizers where the angle between them is 90 degrees, and that's why it's black right there. No light gets through there. Two polarizers where, so the light that gets through one polarizer will decrease by a factor of 2. But if you pass that light through a second polarizer, it actually doesn't diminish it anymore. So for this example, the light through two polarizers is has the same intensity as the light through one polarizer. And then it decreases gradually down. As you increase the angle from 0 to 90 degrees, you can block out all the light. Okay. So yeah, a lot of these problems are just games with playing with cosine with these two rules. I'll post a link in the description of. So one of the most common applications of a polarizer is with sunglasses. So a lot of times light that reflects off of a lake or a pond or something, it will be polarized in a certain direction. So you can wear glasses that will block out light in that direction. So it'll be so that sunlight that reflects off is linearly polarized in a certain direction. You want to block that out. So if you wear polarizing sunglasses, you can block out all of that glare from the lake. So that special angle is called Brewster's angle, if you want to read a little bit about what that angle is. Yeah, so, but there are obviously many other applications of this. Okay.